Time for work, guys. Come on, I need your room. Come on, need your room.
Let's go.
Come on, guys.
Let's go. Yeah, can we take a break? We've been typing code all morning. The yellow lines and we fill it up with the rainbow.
Spies.
Hi, everybody. Welcome to our developers panel. My name is Nick Gunsman. I am the EOS product manager. With me here at Baltimore Center Stage is Matt Halberstadt, who is our technical product manager. We have a panel of parts of our development team. There are dozens and dozens of people who work on EOS every day, from software to hardware to manufacturing. But we wanted to spend some time just talking about what it takes to get one of these consoles from we should make a new console to actually out to a launch day and to release. I want to introduce some of the folks that are with us here. Alice Khan is a senior software developer. She is been with us for many, many years. So hi, Alice, thanks for joining. Dan Duffy is another software developer of ours, team lead. Thanks for joining us, Dan. Max Schweiner is one of our electrical engineers. Thanks so much for joining, Max. And also with us is John Roshi, who is one of our industrial designers. So a pretty wide facet of people that help us get through this process to give you these final results. So I want to start off by kicking it off to Matt. Where do we even start with thinking we need a new desk?
Well, first is the age of the current platform that is being produced. Beyond that, we look at the things that worked, the commentary back from our customers, what they liked about it, what they didn't like about it, areas we could improve. And we really start at that point with line drawings of, it's a lot easier to put pen to paper before you put metal to production. So we do a bunch of iterations and reviews, internal reviews, external reviews. And then after that point, we have a marketing steering team that you and I are both on, and there are many other people in the company that are on, and we say, we think we know what it is, and we present that idea to them. And they say yay or nay, or give us additional feedback. But after that happens, we really then bring in the development teams at ETC. And we start generally with a huge kickoff meeting of bringing everybody into the room and say, this is the idea, this is the goal, this is where we want to be. But still not too much has been determined of exactly what's going to be in it yet. There's going to be lots of portions of development in the different areas that we want to explore and iterate on. Many times we have more grandiose ideas than what we actually bring, but that's not a bad thing. That continues us to bring that development forward in future products. So generally, you know, after everybody sees those line drawings, I'll take it to an example of just the iteration of how even the articulating screen happened on Apex. So John Rashi and a couple other industrial designers, myself, we all went into a room and we said, you know, we want a very useful and practical way to articulate the screens. And we looked at external resources, everything from like Microsoft's Surface Studios to just even plain laptops, and basically put everything out there. And then, you know, with that sort of guidance and idea of what we want the product to be, John Rashi and the other industrial designers really go to work with the mechanical engineers to make sure we can actually do it and the iterations there. So I'd like to hand it over to John Rashi for a little bit to have him discuss sort of his process behind the articulating screen on Apex.
Hello, everyone. So this whole process, as Matt started to introduce, it was very rough around the edges, and the whole goal was not just let's make something new and cool and different, but really provide a benefit to the user throughout the whole process. So a large mega consideration throughout this whole development process was the ergonomics of this screen. Not just make something that can move because that looks cool, but the utility of bringing it forward, changing the angle. What if you're in a situation where it's an outside show where the light's coming down, or you just don't physically have the room to see over your console because your booth's way up high? So all these kind of considerations really influenced not just we want to have a moving screen, but why we want to have a moving screen. And then as we went through it, how to make it move, how to do we want to limit the rotation to always move when the angle moves, and all these different interactions that we ran through with some users at our kind of beta sites and things like that ended up allowing us to create these like really rough models. They're plywood with friction hinges and 3D prints and plotted out consoles, and we went through a few of these buck models, these cardboard and wooden things, to really kind of establish, well, how far can the user reach? Where would it make sense to have grab points? And so moving from pen and paper to plywood and glue was a major step before we even were really kind of verifying exactly what this console was going to be, but it had user input kind of influencing the ergonomics and the physicality of this console right from the get-go.
Well, and I think that that's something that's really useful for, you know, ETC visits trade shows every year. We visit a lot of venues. We take a lot of that user feedback. And so it's really interesting in this part of the process, from my standpoint, who's often out in the field, interacting directly with programmers and designers, taking their feedback in, bringing that in-house, to start to see the mechanics of things being figured out. You know, okay, we have this feedback of, well, a single pivot point, we can't do a lot about reflections. Okay, well, that's something we've brought in, and seeing the mechanical team actually, like, you know, not folding a piece of paper, but starting to move into the mechanics of something is a really exciting step in that process.
Yeah, and just a reminder, this is before we've selected any of the components really for the development of what this is. And after we start to do that, then we have to, you know, do it basically again with using the real components that have fed into all these data points that we received from doing those physical models.
So I'm interested in exploring that because we have a lot of new technology on this desk. We have things that have been a part of the EOS platform for a long time that are just sort of rethought and recrafted. We walk in with a pile of feedback, with a bucket of like, here are things that 8 years of working with TIs has told us. Where do you even begin with we want to do something old, something new, completely think outside the box? Where do we start?
So one of those items, we'll just quickly again on the displays. Knowing that we wanted the displays to articulate the way they did and do, and knowing the feedback that we received from TI and Geo, we looked at what was available for viewing angles, and you set that as a success factor, a critical success factor, and you're identifying these critical success factors for each area of the desk to determine what is important. So we'll move on to another portion that users really interact with, and the encoder design. So the encoder keycap design is brand new to Apex, but the encoder underneath it is the same encoder that is on TI that provides that haptic functionality. So we take that something old that people like, the haptic encoders, but how do we change the interaction with it and building on the small iterations of feedback that we receive? So I don't know how many different encoders we went through.
Yeah, John, I saw that that bucket of encoders on the release video. How many do you have a count, or is it just a lot?
It was in the bucket in the video, there was well over kind of 50 iterations, but under each kind of idea, there were a lot of little variations and backtracks and things like that. So that 3D printer was going all the time.
Well, and so then we move from like 3D printing to quick turn machine components like what John is holding there. And then we explore the materials that are used. Is it going to be aluminum? Is it going to be stainless steel? Is it going to be injection molded? And we start to build that up, you know, involving the mechanical engineers still of, you know, it would be great if we use this technology, but if we can't manufacture it, then what good is it going to do, you know, in the long run? So all those considerations go into it as well.
Well, and I remember very early on in the process when Ann was still product manager, you and Ann came out to New York, and John was out there as well, and just setting rows of encoders in front of some users and just walking away and having them do some feedback and say, okay, what do you need? What do you like? So getting that interaction from the users too is, I'm sure, part of it.
Absolutely. And we try to set it up in the exact same way that it will actually be used in the configuration. So Mike Ritzky, who isn't on this call, is one of our primary mechanical engineers. He and John were working hand in hand to help get these demos, and we would ship them out all over the world to get that feedback. But even other things, when we started to interact with the wrist rest is another example where we took things that we had learned from past on Geo, TI, even back to, you know, Ion Classic, which didn't have a dedicated wrist rest, and the feedback from users, you know, the rake of the face panel. These are all things that developed into what you see here on Apex after multiple iterations. And then the additional consideration of when we got to this point in the project, we decided, you know, it can't just be one console. How do we expand this across multiple consoles and have it keep a similar look, feel, and functionality? So John, why don't you talk a little bit about also the development of the wrist rest and how that came to, and all the calculations you did and iterations of design on angle and feel to get where we got today.
Sure. I mean, the process started out very hands-on with me and Ann Valentino, who a lot of our customers might know. She really helped introduce me to a lot of different places our consoles are used and the different ways they're used: standing, seated, leaning over, depending on booth situations. So it really informed me that there's a lot of different ways people use a wrist rest on a console. So as mentioned before by Nick, we kind of have a two-plane system, one that helps kind of catch your hand and lets it rest when you're using some of the buttons that are closer to you, but also a nice lead that allows you to bridge over and reach further away things, as well as longer sections that push forward onto the work surface, allowing you to get better access to that whole programming section. So Ann and I went through this process of feel and material softness and hardness, and Matt and I went through the process of the material science of it's got to be durable, and we were hitting things on corners of tables and really trying to damage this to make sure that we didn't end up with any wear and tear issues going forward. But one of the unique things that we really wanted to kind of create this sense was this: all the consoles are the same, they're just different sizes. The small, the 5, the 20, they're the same console. They are EOS Apex. And in order to do that, we wanted to create a sense of familiarity with these wrist rest sections, allowing you to, if you go to a different size console, just by feel, you know where your hands are. And when you move them forward, those same keys are there. So in doing so, we kind of actually like created a color-coded system here of different sections mean different kind of zones. And what that also allowed us to do was introduce modularity with that wrist rest, which would help kind of save on cost and production. But at the same time, it gives the user that visual linear delineation of where each section is, and then the feel as well when you're going back and forth in the dark to know where your hand is located. And that modularity influenced the mapping of all of our keys on the console, because changing from one size to another, you still want to be able to have the same consistent key sections to create that familiarity. So any desk, no matter if it's a 5 or a 20, you have that touch and feel familiarity and be able to just go right ahead and use it.
Yeah, and like what one of the things that you and I talked a lot about is sort of the starting to fit those pieces together, right? As certain components get decided upon, as we start to make these decisions, that starts to have a chain reaction through the rest of the architecture of the desk.
100%. And as we're identifying those components and items that we're going to include, like we kind of mentioned, as we start to actually put pen to paper on every individual section and finding the components that will be used, that continuously drives additional iteration in the mechanical layout, in the spacing and connectivity. So, you know, one of the next steps, and I'm going to bring in Max on this next portion, is the little lights replacements are book lights that we have included into the end cap. Now, this is one portion where we came up with a feature, a very simple feature. Let's add some built-in task lighting into the end caps of the desk. It's a great feature that customers can use. Well, that now is going to involve industrial design, mechanical design, as well as electrical design. So, you know, figuring out all these components. So I'll let John speak a little bit of his work on, you know, the industrial design of the end cap, and then, you know, bringing Max into it of selecting, you know, the the LEDs and wiring and getting this all to happen in a tight space. So John, take it away.
So as the industrial design team here approached the end caps, there were kind of a few different goals. One was the ergonomics of adding handles. One championed by my previous partner here, Zach Slavor, the beautiful aesthetics, really trying to introduce that stately, permanent, powerful, strong, and robust feel that we like our consoles to give, because they're working, they're going to keep working for you. They are solid consoles to use, and we wanted that to come through in the physical aesthetic appearance. So Zach's beautiful design here, blended with some of our kind of heritage designs pulled from the EOS TI, actually gave us an opportunity to add a technical feature. That ledge on the side provided us the ability to hide a script light that would aim down and provide a book light area just to the right or to the left of the console. And in doing so, we also had to, again, not just consider how great it is for the user to have a little light, but realize not everyone uses these consoles the same. Some consoles are in the house. How do you make sure you're not blinding the audience members that are sitting to the right of the console? So then we used a lot of our shuttering knowledge here, and we incorporated that into the design. So you actually have to go down well below the work surface level in order to be actually able to see the LED elements on that book light. So you have an amazingly controlled cutoff, which allows you to use that even in a in-house situation. So when we were working with the electrical team to kind of tweak LED spacings, do we need lenses? You know, I need the board to be here. It was a uniquely back and forth and close interaction between not just the designers or the mechanical engineers or the electrical engineers. It was a vortex of like back and forth and this and that in order to tweak it to be just right and make sure that that user was championed while also fulfilling all the technological requirements. So I can let Max take that away.
Yeah, and actually, Max, before we jump in there, you know, we can expand this to almost anywhere on the face panel or inside the console. These same interactions happen on everything. You know, with our new haptic displays, you know, getting the connectors the right height, just spacing of the boards, getting the components on the boards. You know, we want it to be as small as possible. And you know, that sort of vortex, as you mentioned, it's a perfect term for it, because it is constant. You change one thing here and it changes everything mechanically, or you know, you can't have the connector here because when the console is closed, there will be interference from a mechanical thing. So yeah, Max, I'd love for you to discuss, you know, after we've selected some of these components, or we've decided that we want to have a keypad with a display, you know, what are the things that go through your process of, you know, getting that to a functional piece of equipment that we can include on the face panel or in the hardware?
Yeah. So a good lead into that is, you know, anyone who's toured our factory and facility here probably knows this, but ETC really is an electronics manufacturer, right? We do a lot of that from the ground up at the design stage. So we have a really talented team of component engineers and librarians and PCB layout staff that are all kind of under one roof, which is somewhat unique to electronics manufacturing. So when we have you know, a task laid out for us following through the electrical requirements, and we want to build a circuit board, we can pretty rapidly go through and cross-reference components that might be available in our library already. Or if we need to bring new things in, we have a dedicated team here who can get those components in for us and filter them and parameterize them in our library. And we can prototype either right away with something that's form, fit, and function right off the bat if we have that information from ID and mechanical, or we could make a proof of concept, and we run those assemblies on our own lines in the building, and we can iterate and prototype very quickly. And that's a real boon to making things that will really serve our customers well, because we can go through as many iterations as we need to. It's a thrill when we can get it right, you know, very early on, but you know, we don't shy away from doing it until it's correct.
Absolutely. And so in some of the other launch videos that we've been playing today, you can see actual pictures of consoles that we call Silver Surfers.
Yeah.
It is basically just the raw panels of the components that we think are going to make it to the end game. But we just need to get them all together in one package, and the iterations that happen there. So of course we don't make the LCDs or anything like that. We have strong partners that we work with to bring those things in. But we will take in a Silver Surfer just that raw LCD before there's even a touch screen or anything on it. And this allows us to bring the component in, sort of see how it fit and feels, or if we need to make any changes. Another example of that is these buttons, the OLED target keys. We don't manufacture that button. We manufacture the PCB that the button is on, and we assemble it. But we didn't like the feel of the button. So we worked with that manufacturer, and they were very open and understood our concerns. And they said, yes, we will do this. We want to be a partner with you. And that we find those partners throughout all the components of the face panel and electronics and metal and all these other things to bring that experience to you. But it gives us that quick iteration of being able to get these components all in one spot, because there's additional things we as a manufacturer have to worry about. And that's providing you a safe product, a product that will be reliable. And there's government regulations that we have to follow and adhere to make sure that it's safe. So Max, why don't you discuss a little bit of the process behind that as well of, once we've determined this is the real thing, the work we have to do to bring the entire package together just from a hardware and electrical standpoint for safety and other regulatory things.
Yeah, it's definitely exciting when we first get our working prototypes up and running, and there's a lot of energy in the building, and people get rightfully excited, but there's so much that isn't really seen on the back end. Part of that is product safety, like Matt mentioned. That all happens here in the US mostly. We contract with labs who verify and validate our products to safety standards. And then another one is all of our electromagnetic compatibility. And that's generally strictest in Europe, but we strive to design all our products under one variant for the global market, which will be the case with these consoles. So oftentimes we do take prototypes to a partner lab in the UK to perform all that work. With travel being a challenge recently, we did that here in the US, but I personally driven some of these consoles back and forth to the Chicago area to the lab to solve problems that our people don't necessarily think of and see right away. But when you're in a show with the desk, you don't want any hint of a worry that something's going to interfere or the console is the cause of some problem that, electrical gremlin you're going to have to chase down throughout the venue. We really make sure that doesn't happen.
Yeah, and I'll mention a lot of this happens, and these board PCB bring up happens in such a way that our software team hasn't even seen it yet. So Max is helping bring up the individual PCBs so that we can get a firmware developer to actually start hooking up all the internal components. And some of that, there's a lot of, high frequency signals that are going through here. So even that is done sometimes with external resources or internal design resources, but it's very specific. So Max, why don't you talk about some of the high frequency, high bandwidth connections that we are utilizing in Apex that are completely new and current technology.
Absolutely. So one of the big ones at the forefront is our DisplayPort interfaces. So we support 4K displays across 6 monitors, 3 internal and 3 external on all of the Apex consoles. And that's really high speed signaling. It's the fastest signaling we've done on any product that ETC is producing. And it's something that's now relatively common in the consumer space, but to get that to a point of reliability in a commercial industrial market, it takes a lot of work. And in fact, we did spend a lot of time both on signal integrity for those display interfaces so that that they're going to be reliable. And also from the emissions side, making sure that they're not going to cause lots of high frequency hash and things that are going to interfere with wireless mics. those edge rates are really fast on those signals, and they definitely have the potential to be playing in the same space as wireless communications. So yeah, that was definitely an exciting one.
Well, yeah, and there's additional, like Max mentioned, there's lots of consumer products that are out there. But again, we're not going to put the consumer product in our equipment. But we want to bring the advancements of the consumer technology into the industrial world. So even things like our carrier board supporting all that I/O that is unique to our industry, getting that connected and available is sometimes a task. And sometimes we have to, again, partner with industry leaders to help configure things to our specific needs and sources and use cases. So Max, why don't you talk a little bit about the carrier board and some of the unique things that are on it? And for those, the carrier board is the equivalent of the brain of the entire thing. It is where our CPU lives. It is where our GPU is. So go ahead, Max.
Yeah, so obviously we're not manufacturing our own GPU and CPU. We have to rely on big industry players like Intel and AMD to help us with that. So our carrier board is the largest piece of electrical hardware outside of the screens that's buried in the console, and it hosts the computer on module, which has the CPU. It also hosts a modular GPU, and it fans out basically all of the special peripherals that we want that are pretty highly customized for this console. There's a lot of USB going on internally. So, we have to take that from PCI Express directly off of the CPU and break it out into USB interfaces. We have lots of Ethernet control on there. So we've designed in custom Ethernet circuitry to give you those 4 independent NICs. And I'm trying to think of what else there is, Matt. Do you have any other ideas?
Yeah, SFP plus
on the spot. Yeah,
the Wi-Fi, the Bluetooth. Yeah.
Oh, right. Wi-Fi and
there's
Bluetooth too.
There's a lot going on, but this is another example, though. Max just mentioned the wiring internally to these things. There's a significant amount of connectivity and interconnectivity that needs to be robust and provide all the different aspects of control in these consoles. And when we look at that, the articulating screens is another example of the two departments or multi-departments working together to make it become a robust solution. So Max and John and Mike, our mechanical engineer, working on the design of the arms to even support the cables inside and doing the testing for the different cables and make sure that it will be reliable as you articulate the display and we're not harming any of the cables or interconnects.
Yeah, and I think, as mostly a software and features person, the detail that goes in every day over a 5-year period to get all of these elements to function, to be reliable, to interact together is really something that is hard and time consuming. We actually had a question from our YouTube chat. Amy is asking, what are your views on those who make custom hardware surfaces for Nomad and any improvements on OSC to help us put out some new toys? I think we have a lot of makers out there. We support our maker market. 100%. Not everyone has a 1,200 person manufacturing plant with a large staff of engineers to spend 5 years to pull something like this together. So we're always interested in extending support for homemade kits and things that will help you do your job. So I think that that's something that we can look forward to. A reminder that if you have questions as well, drop them into the chat. We'll try and get to as many of them as we can. So to transition, so we have this thing now.
Yep.
We've spent.
It doesn't work yet.
It doesn't do anything.
It doesn't do anything.
But it all plugs together and it looks great. So
yes.
Where do we go from here with this big box?
So then, we hand it over to and work completely hand in hand with our firmware development team and our software development team, as well as throughout the entire process, we're working with our manufacturing folks to understand the different intricacies of every area of the console. So including like paint and things like that, going through the paint line, getting up the vendors set up. Yeah, once we have the big old box and all the interconnectivities, we need it to start running. We need it to start doing what it's intended to do. And the base of that for us is Windows. This is a Windows embedded PC, the Windows 10 specifically. And there were lots of things that we wanted to do differently from our interactions with Windows 7 and XP over the years. So we wanted to look at ways to make it a little bit more robust in the field, as well as user-friendly for our manufacturing folks. So I'll let Alice speak a little bit of getting up to speed on Windows 10, building an embedded image on a platform, and sort of everything, all the details that you need to do there. But the other interesting thing that Alice can speak about is some of the built-in self-verification that we can do to that process to make sure it's repeatable and dependable for many years to come.
So one of
Alice.
So one of the big things that we wanted to focus on with designing the Windows 10 image for EOS was that no matter what console you're on, it feels exactly the same across the board. And so it doesn't matter if it's a Apex 5 or an Apex 10 or Apex 20 or Apex processor, they are all running the exact same Windows image on the back end. And so we start with a Windows IoT embedded image, which is your stock Windows 10 image. And then we run it through a fairly rigorous set of customizations. So we set registry settings. We make sure that all the drivers are installed, all the language packs are installed, that everything is exactly as streamlined as we can possibly make it. We make sure that there is a built-in factory reset so that in the field, you can immediately flip that toggle if you need to, and you're back to exactly how it came out of the factory. And then after all that's done, we capture that image and apply it to any other device that we need to. But the benefit of doing it this way is that we can repeat this process over and over and over again, which allows us to do very quick iterations for, obviously very complex systems. But to make sure that we're still hitting all the check marks that we need to do, we spend a lot of time working in verification tools to the base image itself. So it checks to make sure that the drivers that we installed are actually installed, that the registry settings that we changed to make sure that touch support works, those are actually still in effect too.
Absolutely. And, there's sometimes a lot of custom verification and needs that happen within Windows. So all the different drivers, as Alice mentioned, we need to include them in the image, and then we need to make sure that they are verified working and provide all the details that we need. And again, just the iterations of customization to make sure wake on LAN works, to make sure the displays are identified properly, to make sure we expose all the settings that are needed for the network connections. All these things is an individual element that needs to be consistent every single time. And we go through and connect it, as well as all the individual drivers for the devices that are connecting to the host, and making sure that that is robust and dependable.
So Alice, is it fair to say that we're using this embedded environment to start to tell EOS software when we get there what these devices are and how we expect to plug into them, interact with them? Is that sort of a generalized assessment?
Yeah, absolutely. So by creating the Windows 10 image for the consoles, we're creating the sandbox that the EOS shell and by extension EOS can actually play in and thrive in. Without having that image in place, EOS doesn't know how to talk to any of the devices. It doesn't know how to run on the system. So this is kind of like that final step between hardware and software that needs to happen to make everything work.
Yeah, absolutely. And not only that, this is the portion that we're also developing for our factory for production. This is the component that they put in all the devices after they've connected. We've made all the PCBs now, and now they're putting it all together. When they put it together on the factory floor, this is the portion that really brings it alive and connects all those dots.
Excellent. But it still isn't an EOS
but
yet.
It's still not an EOS yet. No.
Where are we?
So that after we get that, we have the best development team that there is. And we have many EOS developers, including Alice and Dan, that then get all the bits and bobs. Most of the time when they start to see the hardware, they get like this individual component. Like we know this is good and sorted, and we will send that out. I know Alice has had just carrier boards with a power supply to start to develop that Windows image. And again, to start developing the software on it, you will get just this section of it so that they can really focus on that one particular thing. But I'll let Dan Duffy, sort of jump in and talk us through from his side, what starts to happen after you receive that piece of hardware. How do you make it EOS? How does it extend into the EOS family? So Dan.
I would say there's two main components to this when the software engineers get involved. One, you get all the different boards that have all different, more encoders and knobs and buttons and everything that we have to interact with. That's all makes up the console. But the other part of it is all of the different displays, because as probably the main thing that all the software engineers see when we first, saw drawings of what Apex was going to be is that is a lot of monitors, a lot of displays. And, I think we were initially looking at like, is that 60 monitors on it? When you see all of the target buttons as each a monitor, it's very overwhelming. So even very early on, we spoke of like the amount of work that was going to go into Apex is getting content on all of those displays. So there's, technological hurdles to just at the speed that we run, being able to, deliver content at 4K displays for all of these and for all the buttons and having everything update and everything. But then the other parts of it is just like all the additional user features to make everything that has been running on EOS for, like after 15, 17 years of development, there's just a lot of content that you want to be able to work with everything. So like the example that I like to give is like the encoder display. We have 8 new encoders or 9, 8 plus a config encoder. And from, the outside, when you first look at it, you say, oh, there's 8 more encoders, and the encoder display is a little larger. But I can't imagine how many months we're spending to how to make fit 8 more encoders worth of data on a display that is larger than the TI display. But, there's so much room, and you're constantly having decisions about, do you want more information here or less information here? What should pop up and what should hide? And the whole process of that, I think anybody could understand that aside from like a technological, like how to write the code, there is just like multiple iterations with the developer and Nick Gonsman and Matt and Test, everybody seeing an iteration of something and deciding, it's just too much data in this small space. We need to, move this around and shuffle this around, and this needs to move to a pop-up. And all that goes through another iteration. And those kind of iterations can just go on and on and on as different people get involved when the bar is perfection, when the bar is that giving it to someone and saying, is there anything that could improve on this? Do we need to rearrange all of this, and that's just one display adding 8 new encoders for it. But there's similar things across new hardware with all the displays that we have. And some of the big items that were significant software development, so like the target buttons, of course, just led to a huge feature expansion on direct selects that everybody gets, even if they don't have an Apex, because now you can have an image attached to every target that helps you even for the direct select tabs. But that's part of, because we have all of these that can show the target buttons that can show images. The keyboard display, which can now show direct selects, or it can show magic sheets, just a lot of iterations of that as to, we have this amount of space, what all is useful to put in it, how do you configure it quickly on the fly. Haptic button feedback, where you press the soft button and you get that thump back. How does that work with double press and drag and magic sheets? Just like an enormous amount of iteration when you're trying to set that bar of perfection.
Yeah, and I think certainly from a software specification standpoint, that's it, and you can extrapolate that to those million decisions, those million iterations that we have on that one area of the desk that expands to others, and all the while making sure that those features where we're able to are available for other users on other platforms. That the redesign of the screens for like the encoder display still looks good on a TI and on an Ion Classic. So there's certainly a lot of work that we do with the software team to make sure that we're bringing features not just for the newest hardware, but also for the entire family. I want to pivot to a question that came in real quick. You had mentioned verifying monitors, Matt.
Yep.
Specifically the internal ones.
Yeah.
What's the process of ensuring that those are consistently assigned and making sure that we
Oh.
know what's happening at each moment?
So we control that on a couple of different ways. So there is this technology behind the scenes that does display identification. It's called EDID, short. So we use that. Each individual display has a unique identifier so that we know exactly where each one is. We then also use the routing of the graphics card. And because we connect the graphics card through our carrier board, we know exactly which port is which. So we can use both of those things to help navigate what is what. And we tell EOS what those are. So EOS, when it starts, it identifies and it goes, oh, I know this is the primary display. EOS knows each and every single one of these consoles. EOS knows every single component that should be on a console. So if we say that is an Apex 10, EOS is going to throw a code or error and go, this isn't right. Because, during the process, we're expecting every certain aspect of these things to be just right. And it's a lot of work. It's a lot of information to, filter back through, but it's what we do to make sure it's a consistent experience every single time.
Absolutely. We've got just about 10 minutes left, so I just am going to jump in with a few more questions. Thanks of you for posting. Can you just talk quickly about the Haptic technology on the encoders and on the touch display, and sort of how they work? Like what is happening under there?
Sure. So some of it we're not going to get into because it is patented, but it is something that we can discuss on the outside without going into the minutia of the details. So this is a electromagnetic encoder. So there is a electrical field and a magnet that we can control that goes through it. We send very specific signals to it that says, hey, do this. And as you can imagine, a magnet that you can control, much like a car dampener that has a variable softness and ride heights and stuff like that, we can send similar signals to this to say, oh, make it click now. So it goes click, 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 or make it turn that off. So just act as an encoder. We're actually working with the same companies that do like the new DualSense controller that is on the PS5. Like that is the exact same company and technology that we're working with to provide these sort of features back to our users. The haptic display is something, very new. Haptic encoders we've had since EOS Classic. A lot of people, might still not know that that's a thing, but they have been there since EOS #1. Yep. And we're happy to continue because of the benefits that offers. But the haptic display is brand new technology that we help bring to the market. This actually sits on a bed of force sensors and a couple of physical actuators. So the display itself is physically floating, and we are using the multiple sensors to interact with the firmware that's built into it. So we know when you're touching it, we know when you're pressing it, and using that information, we can actually physically bump the display and have it physically move. And that's something we've been looking forward to, including for a long time. If you look at EOS Classic, the the displays keys that were on there to try and give that same tactile feedback, because we want your eyes to be on the stage, on the performance, but we also want you to know the thing happened that you intended to happen.
Yeah, exactly. And that's something that I think certainly from a software and an operator standpoint, being able to start taking those twinkle of ideas that our mechanical engineers were looking at 15 years ago and came up with like the button overlays to get those mechanical things out of the way of the screen and allow the screen itself to be mechanical is pretty exciting. Is there any new exciting possibilities now that we have Windows 10 under the hood that Windows 7 didn't or couldn't offer?
Absolutely. So there are certain things that we're looking at. One, the security advancements that Microsoft will continue to provide security patches. And as we look forward to a future where there's more connectivity to the outside world with consoles, that's a really important aspect to keep in mind. Additional advancements are using, of course, more state-of-the-art processors, state-of-the-art features, but even that built-in factory recovery tool that is here in Windows 10, that some of the advancements in Windows to allow us to do those or give us the tools to provide those options. But using newer technology is a significant advancement too. But it does have some really cool built-in things. Now that we have Wi-Fi and Bluetooth built in, exposing those in a different sort of way in the tools that Microsoft has already built for the consumer world. There's a feature called Pair My Phone, for security locking. We could use that for a similar sort of feature within EOS. So we know when it's connected to the desk, you walk away. We could have the desk go to its own lock mode. And using the IoT version of it, Microsoft provides us all the hooks to get to those features directly.
Well, and I think that's just, it's simple enough to say like Windows has 10 more years of advancement from 7 to 10. There's a lot more stuff available for us to look at in the future. And I think that's sort of the theme of a lot of this hardware. If you joined us for some of these other sessions, is that putting things in that we can work and unlock for years to come with software updates. This is a fun one from Tyler. Duffy might want to chime in on this one. Are there any lines of code that are still the same from EOS 1.0?
Yes, I'd say a pretty high percentage actually. 'Cause I mean, we've been writing it for about 17 years. I asked one of the developers just earlier today to just run a line count on our project, and it's 5 million lines of code. So even just the amount of typing that we've done to write EOS is kind of funny. But yeah, there's a lot of it that, things that we wrote, for certainly even the first 5 years, if, they still work fine, they don't get rewritten. A lot of the stuff that gets constantly redone is display code, just because, like most recently switching to 4K displays, but there's always changes to colors, to, the look of EOS. But there's other things that, are largely untouched for, unless they need changing.
Yeah, excellent. Yeah, it's,
so maybe 1 million of the 5 million lines.
I think one of the things that we talk about internally pretty often is, the Fade engine is the Fade engine, right? There's a lot of things that are under the hood that are, purely operational to EOS that are sort of fundamental. And so long as we don't need to shift any of the way that those core features operate, or we don't bump into them and make some errors, those things can keep trucking on. So another fun one that has come in. Will the new consoles be able to run multiple instances of Augmented on the same network? So a bit of clarity. Each device right now can only run one Augmented session, but if you have multiple devices on the same network, each individual one can either run it internally or with a tether. So we do allow that now. But do you want to talk a little bit about sort of the headroom we've left ourselves for software for the future?
Sure, absolutely. And that goes within all the different components of the Apex console. Like you mentioned, we expect these things to be around for 7, 10 plus years. So we engineer that on the durability side, on the electrical component side, but additionally the feature side that we can continue to expand and add these sort of things to it. You know, there's you know, the entire backlit display and our keys that are 100% RGB, just the future thinking of, you know, maybe we might want to use this one day to do other things or to change how you interact with it is that sort of thing. And we add that into the computational side of what is under the hood, because you think about it, it's pretty cool that a EOS TI that, you know, started 7 years ago can run augmented when it was never thought about on it, right? Yeah. And it's because we had, you know, at the time of TI when it came out, those additional considerations. So like the GPU is 4 times better than anything we've ever had in any EOS product. The CPU, there's more cores, it's faster than anything we've ever had in any EOS product before, including things down to using the latest in technology. Again, I'll probably nerd out a little bit, but even communication to the hard drive. You know, we're using PCIe NVMe hard drives in this, not because it necessarily needs it today, but we want that headroom for it in the future.
Yeah, absolutely. So we're almost out of time. So I think that is a great place for us to wrap up. I want to say thank you to Matt and our panel for being here. Thank you all, folks. I really appreciate it. We want to thank the beautiful and courteous Baltimore Center Stage and their team. Michael, thank you. Travis, Tamar, we really appreciate you hosting us. And thanks to the video team, the marketing team. They're the ones who put us in front of you and us talk.
Make us look good.
Absolutely. So these are new machines. These are new functions. As you kind of have gathered, we like to nerd out about it as well. So feel free to get a hold of your ETC rep or local dealer. Feel free to reach out to us on social media. We're always happy to nerd out with you as well. We will be at USITT. That's what brings us to Baltimore. So if you happen to be in the area, you can come put your hands on these immediately. Also, during our launch video, you may or may not have seen that we did a revamp of the EOS side of our website. So please check that out. There's data sheets, tech specs, all the things you need about the new consoles, and also a new area for EOS users called EOS Home, which is a collection of all the stuff that sort of used to be scattered about, is now in a centralized place. So thanks again for spending your afternoon with us. We can't wait for you to see these things out in the wild, and have a lovely afternoon. Thanks, everybody.
Thank you.